3C is about means and medians, although I kind of rephrased it to be about measures of center, since that's what means and medians are. There are other measures of center besides that, like modes and mid-ranges and things. But the general idea with a measure of center is it's supposed to give you a value that represents a typical value for that data set. So which one should we use? Because they're not all going to be the same thing unless you have a data set that's perfectly symmetric, which that rarely ever happens in real life. So the most common measure of center or measures of center, they're ones that I would imagine everybody's heard of, the mean, median, and mode. The mode is actually covered in the next section, not in this one. So it's kind of referenced at the beginning here, but then it goes away. And sometimes there will be a measure of center that's better than the others. And it depends on things like what kind of data you have, because if you have qualitative or categorical data, the only thing that you can use is the mode, the most frequently occurring value. Right? Like if you have categorical data where you have non-numerical data, like if it's like the states that people were born in or something like that, you can't average those, right? Like, Alabama plus Alaska plus Montana plus California plus Arizona divided by 5. Like, I don't know what that means, right? No one does. And the median doesn't work either. So the mean and median are for quantitative data. And the mode, you could use it for quantitative data, but it's most useful for categorical or qualitative data. Other things, like if there are outliers or depending on what the shape is, where I know that's getting a little bit ahead of where we are right now, but like if you have a shape that's symmetric or one that's skewed, where basically if you just think of skewed as being not symmetric for now, that's the right idea. It's something that's clearly not symmetric. But then let's see, individually, the mean, it's the thing that's the average, right? Like those words, if you want to just kind of think of them interchangeably, I mean, they are the same thing. It's you take your data values, you add them up, you divide by however many there are. It doesn't have to be an actual value in the data set, and if it's not, that's fine. So like if this was your data set 20, 21, 22, 23, if you average those 4 numbers, you're going to get 21 and a half. That's not a value in the data set, but that's totally fine. And then rounding, the rule of thumb is to go one place farther than the original data, at least that far. So like here, going to the nearest 10th, like you would just leave that alone. You wouldn't round that to 22. You would leave it as 21 and a half. If you go farther than that, there's nothing wrong with doing so. I guess here that wouldn't make sense. Like you could go an extra digit, it's just adding in a 0. But if it's one where you weren't dividing by 4, like if you were, dividing by something where it didn't divide out quite as cleanly, then yeah, you can round off farther out if you want to. There's nothing wrong with that. Let's see, the median then by comparison is the midpoint when you put the data in order. So I guess that's the first thing. If your data set is not in order, you got to do that first. You got to put it in order. And then it depends on if you have an odd number of data points or an even number of data points. Because if you have an odd number of data points, once you got your list in order, there will be one right in the middle. That's your median. Then if you have an even number of data points, you're going to have to average the 2 that are in the middle, like the 2 that are the most central. But, I mean, that's only like a tiny little bit of extra work. So, all right, figuring out medians. So the top one's got 7 data points in it, or 7 observations, and then the bottom one's got 8. All right, so this one here has 7 observations, and then this one down here has 8 observations. All right, so this way we get both techniques in there. First things first, we got to put them in order. I tend to cross them out as I'm writing them in. So like I'm going to write them in order underneath. So the smallest value is obviously 4, right? That jumps out because it's only a single digit. Then after that, let's see, we got a 29, that would be next. Then a 41, then a 44, and then a 45. All right, and then after that, 59, 65 in that order. And there are 7, so there's one right in the middle. It's the 44, right? Because there are 3 to the left, there are 3 to the right. So the 44, that is the median. And that's it. All right, so with an odd number of data points, it's not too bad. With an even number, I mean, this isn't really going to be too intense either. I guess, let's see, 15 and 16 are the smallest. So 15, then 16. Nothing in the 20s. Then we got a 30 and then a 33 in the 30s. In the 40s, we got a 46. 50s, we got a 54. Then other than that, all we got left is 61 and 80. So 61 and then 80. And there are 8 of them. So the 2 that are the most central are these 2, the 4th and the 5th, right? Because around this grouping of 2 that I have with that bracket, you got 3 down here, you got 3 up there. So the median would be the average of those 2. So it's 33 plus 46 over 2, which is 79 over 2, which is 39 and a half. All right, so that's pretty much it as far as computing the median goes, right? There aren't any other possibilities, right? It's either an odd number of data points or an even number of data points. I guess just make sure you put them in order first. All right, then this resistance to outliers and skewness thing, this kind of goes along with, which one would be better, right? Should you pick the mean? Should you pick the median? Well, when you compute the mean, you use all the data values, right? Because you add them all together and then you divide by however many there are. But they're all given equal weight. So that means that if you have an extreme value, like one that's way bigger than everything else or way smaller than everything else, then that's going to affect the mean, possibly by a lot. So that's what being sensitive to extreme values means. It's just that if you have an extreme value, it may have a large effect on the mean. The other way of putting that is to say it's not resistant to extreme values, right? That's just kind of saying it from the opposite perspective, but it's the same idea. So let's say if we were going to get the mean of this. So 1, 2, 3, 4, 5, 6, 105. All right. Well, the mean would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 105 divided by 7, since that's how many there are. And let's see, 1 through 7 added up, or 1 through 6 added up is 21. So 21 and 105 is 126 over 7, 18. All right, and is that a typical value? No. So I would say 18 is not typical. Let's say it's much larger than 6 of the 7 values. And I guess much smaller than the other one, right? A whole lot smaller than that 105. But then you go, well, if it's a lot, right? I would view this as being a lot larger because, I mean, it's 3 times as large as the 6. And it's even bigger than the rest of them. So if it's a lot larger than 6 out of the 7, you go, well, is that typical? Like, that's not really in the middle of the data set at all. And so then you'd say, well, what about the median? The median of this is 4, right? Because you got 3 to the left of the 4 and 3 to the right of the 4, right? They're already written in increasing order. And the 4 seems a little more typical considering what these values look like. It looks like that 105 is just an anomaly. Right? It's just something weird happening. And that 4 is probably a better measure of center. And that's what happens when you have an outlier, that the median tends to work out better. So the median is resistant to extreme values, and that's because when you compute the median, you don't use them, right? The values on the end, they never end up in the computation of the median, and that's where the outliers are, right? The outliers have to be on the end, either on the upper end, like way out on the right, like that 105, or on the lower end, right? Like if you had a bunch of really big numbers and then one little tiny number, that little tiny number is an outlier. But think about it. When you compute the median, either it's just, with an odd number of data points, it's the one number right in the middle, or with an even number of data points, it's the 2 that are in the middle. It's never the ones on the end. So because the outliers never factor in to the computation of the median, it is resistant to extreme values. All right. So then what should you use? If you have a skewed distribution, so like one that is clearly not symmetric, Or if you have outliers, then you probably want the median. Because skewness and outliers tend to distort the mean. The mean gets pulled in the direction of the outlier or pulled in the direction of a long tail if you have something that's skewed. So like the idea for skewness, I guess I could draw these things. And this is getting a little bit ahead more toward like when we start talking about the normal distribution. But that's symmetric, right? Like you have a bell curve that's symmetric. But if you have something that's skewed, there. That's skewed, right? You look at where that hump is, it doesn't stretch out that much further to the left, but then it stretches way out to the right. So that's what skewness looks like. And you can have it go in the other direction too, where you have the left tail being the long tail. But if you have a skewed distribution, the mean gets pulled toward the long tail, so you don't want the mean then either. You probably want the median. And I know the skewness stuff isn't in this particular section, but it looks really weird to not talk about it now. Because this is the other case where you'd have to make that decision, like, is the mean or the median better? And if you have something that's clearly skewed, the median's better. So I felt obligated to put this in here. So generally, skewed distributions, or if you have outliers, you want the median. For something symmetric, then they're actually going to turn out to be about the same thing. But then you're better off with the mean, because if they're going to work out to be roughly the same anyway, the mean is a more thorough computation. So more exhaustive or more thorough, since all the data points are used instead of just a couple. But usually the way it goes is symmetric, no outliers, mean, skewed, or having outliers, median. All right, then this is kind of interesting here. What if you have the frequency table and you need to compute the mean or the median? And that's what we're going to do here, because we can figure it out. You just have to use the frequencies to do it. So the computation of the mean has multiplication in it now instead of just adding, but that's going to be about the only difference. All right, so Greater Yellowstone Today, published by the Greater Yellowstone Coalition, gave the following data about the number of annual grizzly bear mortalities over a 20-year period. I rewrote this and I kind of truncated the language. I could have written that better. What that's supposed to be about is it's about grizzly bears that died, not grizzly bears that killed people. And that's not really obvious from the way that I have that written now. So sorry about that. I used kind of vague language there when I compressed all the wording down. All right, so anyway, getting the mean and the median. I'm going to put the mean underneath because it's bigger. And then I'm just going to do the median like up over here, I think. So how would we compute the mean? Well, if you use just how the frequency table would be constructed, what this is telling us is there are 2 zeros, 6 ones, 4 twos, 1 3, and so forth, right? So what we could do to compute the mean, instead of adding up all the individual numbers, we could just say, well, we can use multiplication. Say 0 times 2, that takes care of the 2 zeros, plus 1 times 6, there's the 6 ones, right? Plus 2 times 4, there's the 4 twos, plus 3 times 1, plus 4 times 3, plus 5 times 2, plus 6 times 2. And we know that there's a total of 20, right? Because it said 20-year period, so it should be 20 years. I guess you could add these up, right? You go, well, that's 12, 13, 16, 20. Okay, yeah, we're good. So let me see if I can simplify this a little. So let's see, if I do all the multiplication, it's 0, 6, 8, 3, 12, 10, and 12 over 20. So let's see, 14, 17, 29. Let's see, am I adding that right? I think so. Let's see. Or am I? Because this is working out differently than I thought it would. 29. and 22. Yeah, because I thought this was supposed to work out to be 49, not 51. So let's see, it's 24, 34, 40. And I mean, it looks like it's going to be 51. All right, so 51 over 20, which should end up being 2.55. So I guess when I ran through it before, I must have had it wrong because I thought that was going to be a 49. Oh well. Oh, I know what happened. Okay. Yeah, I think I had it mistyped before and I fixed it. Okay. Yep, we're good. All right, so that's how you would get the mean. To get the median, let's see here. If I kind of section this off, so I'm going to put the median up here. All right, and maybe just to do it in a different color. So there are 20 observations, right? So if they were in order, then 20 is even, so you need the 2 in the middle, right? So then the 2 in the middle would be the 10th and the 11th, right? Because you'd have 9 before the 10th and 9 after the 11th. So it would be the average of the 10th and 11th observations. But notice what we've got here. We got a 2, then a 6. So the first 8 are all less than 2, right? So the first 2 are zeros. And then 3rd, 4th, 5th, 6th, 7th, and 8th are all 1s. So there are 8 observations less than 2, which would mean that the 4 observations equal to 2 are going to be 9th, 10th, 11th, and 12th, right? If they were in order, that's the positions they'd be in because the first 8 are zeros and ones. So in these next 4, okay, that's 9, 10, 11, 12 in order. Okay, well, we need the 10th and the 11th. They're both 2s. So that means you're going to average 2 and 2 and get 2, right? So I guess I could write this out, but this looks really weird when you average 2 of the same thing, but it would be this. So 2 plus 2 over 2, which is 2. Right? So since the 10th and 11th are both 2, then you average them, you get 2. All right. The other example on this page is sort of an interesting idea. What if you can't get the exact mean? So what if instead of this kind of frequency table where you have individual values, what if you have one where you have classes? Then how do you do this? Because you don't have the individual values, right? You don't know what those 10 values are that are in there. So you can't get the actual mean, and that's why it says that we are estimating the mean. So we've got a random sample of bonuses and thousands of dollars paid by a company to its employees, and we're going to estimate the mean bonus. We're not going to get an exact value because we can't, right? We would need the exact numbers, like the exact bonuses, and we just know there are 10 between 0 and 2.9 thousand, which I guess most people call 2,900. That sort of thing. So, okay, well, how do you do this? Well, what you end up using is the midpoints. So, all right, so we're just going to need midpoints for these first few classes. I guess green, that's fine. So like for the first class, or I guess first class midpoint, it would be 0 plus, you just average the 2 class limits, or the 2 endpoints. So 0 plus 2.9 over 2, which is 1.45. Right? And then the second class midpoint would be 3 plus 5.9 over 2, which would be 8.9 over 2, which is going to be 4.45, and so forth. So what you end up here for the midpoints, you have 1.45, then 4.45, and it's going to go by threes, right? It would be 7.45, 10.45, and then 13.45, right? And it's going to go by threes here because it's going by threes here, right? That's got to match up. But the point here of getting the midpoints is we're going to do something similar to what we did in the last example to get the mean, except since here we have ranges of values, right? We have these intervals. Then we've got to get the interval down to one individual number. And so to pick a typical value for that interval, the best thing you could use for a typical value is the midpoint. And so that's why I got all these midpoints. And then what we end up doing is if we're going to estimate the mean, so I guess I'll say estimate of mean, that it's going to be, so the midpoint multiplied by the frequency now, and we're just going to have that over and over all added together. So 1.45 times 10, right? Since we had the midpoint of 1.45 for the first class, and then the frequency was 10, and same sort of thing over and over now. So 4.45 times 12 plus 7.45 times 5 plus 10.45 times 2, and then plus 13.45 times 1. And I guess we would need the total, but you could get it by adding. It never actually says it in the wording, but if you just add up, this is 30. Since 10 plus 12 is 22, plus 8, that's 30. Right, so we'd be dividing by 30. And what you end up with, I guess after using a calculator to figure this out, it's 4.65. And that's the estimate of the mean here. So notice what we end up doing, like compared to what happened up here. Right, here we had the individual values and we just said, okay, 0 times 2, 1 times 6, 2 times 4, and so forth. Add all those products together, divide by 20, since that's the total number of observations, and you got your actual mean. Here, we're trying to do the same sort of procedure, except that we need to get these classes down to one individual value. And the best typical value you could use would be the midpoint. So you just get the midpoint of the two class limits in each case. So like 6 plus 8.9 over 2, that's 7.45 and so forth, right? That's what all 5 of those are. And then for each of these classes, it's just midpoint times frequency, and you add all those products together, divide by 30, since that's the total number of observations. And that's how you get the estimate of the mean. This, I think, is the most unusual thing that shows up in this section, and I think if you can do this, you can do everything else. So this one, it's relatively short, I think. There are some questions that are just, here's a little data set, figure out the median, or here's a little data set that figure out the mean. But I think this is the most unorthodox situation where you've got the frequency table, but it's got classes instead of individual values. But if you just get the midpoints, then you end up doing something very similar to what you would do if you had individual values.